So, that is why here I am going to write a fatigue failure is indicated here. So, here you can see a fatigue failure generally is indicated here if you can say if you can say your amplitude of shear stress tau A is equal to, you can say, if equal to endurance strength due to shear. S E represent shear, this small e represent shear, E represent endurance strength. This you should keep it in mind. So, what is SSE? Endurance strength, due to shear stress. This you should keep it in mind. This is one criteria you can see, this tau A equal to, once it is equal to endurance strength due to shear, then it is subjected to fatigue failure. Now, for static failure, so for you can say a static failure is indicated, if your maximum shear stress value will be equal to, you can say, amplitude plus mean shear stress of that component. Why? Because we know you can say tau amplitude equal to, you can say, tau max minus tau mean divided by 2, and tau mean is equal to, you can write as tau max plus tau mean divided by 2. So, if you just add these two, what you will get? Tau A plus tau mean, this will be equal to what? Tau max by 2 plus tau max by 2. So, this will be your tau max. So, that is why I have written static failure will be taken place if the maximum shear stress value equal to the amplitude of that shear stress plus mean of that shear stress value. These are the things you should keep it in mind. So, these two criteria you should keep it in mind. Okay, this is, let us equation number A and this is equation number B. These are the 2 points. Based on these 2 criteria, we need to design the component subjected to what it is called fluctuating types of torsional stress. Initially, why mean stress or mean torsional stress do not have effect on what it is called endurance strength. That related some explanation here I have given. Generally, the inception or start of fatigue which result from alternating shearing stresses, and that resistance of the fatigue is influenced by what? Magnitude and sign of the steady normal stress. This you should keep it in mind. That means, the starting of this fatigue due to alternating shearing stresses, it depends on what? Magnitude and sign of steady normal stress in plane of maximum shear stress. This you should keep it in mind. Where the maximum shear stress plane is there, at that shear stress plane generally whatever the magnitude and sign of steady normal stress is there, depending on that thing, generally this initiation of fatigue generally results. This you should keep it in mind. But in torsional case, generally the steady normal stress is 0 in on the plane of maximum shear stress. So, wherever the maximum shear stress is there, on that plane steady normal stress is 0 in maximum shear plane. That is why this steady what it is called, you can say mean shear stress do not have any effect on endurance stress at the initiation of what it is called fatigue failure due to torsional shear case. This you should keep it in mind. So, these 2 points if you just know, then you will get the idea of why this mean stress initially do not have any effect on endurance strength due to fluctuating types of torsional stress. So, in torsion the steady normal stress is 0, 1 plane of maximum shear stress for all value of mean stress. That is why as for all value of mean stress, this torsional you can say steady normal stress is 0. That is why what it is called, it does not have any effect on endurance strength due to torsional case. This you should keep it. Some other point also here I have written. The resistance of fatigue would be increased, generally fatigue resistance increase we know by compressive stress values, and it is generally this fatigue resistance is decreased if it is subjected to tensile types of what it is called normal stress value, that we know. So, and another point also I have written a little bit for understanding purpose. The steady normal stress is directly affected by mean stress. Okay. A compressive mean stress will increase and tensile mean stress will decrease the fatigue strength. That is very common things, because compressive things it generally help to close the you can say fatigue fracture or you can say fatigue crack propagation, whereas tensile things which generally act as a opening of that crack which help to propagate the crack, what I am telling understand. That is why its fatigue strength is decrease if it is subjected to tensile types of normal stress. If it is subjected to compressive types of normal stress, then its fatigue resistance will be increased. That are the things is just for explanation purpose I am showing. So, why this mean stress do not have any effect you got, let this A point and let this is B point, these 2 points you should keep it in mind, because generally always you should keep it in mind the resistance to fatigue is influenced by magnitude and sign of steady normal stress. Okay. That steady normal stress where it should be in the plane of maximum shear stress, but in case of torsional case in the plane of maximum shear stress the steady normal stress value is 0, negligible you can say, on plane of maximum shear stress. This you should keep it in mind. That is why for all values of mean stress generally it do not have effect on endurance strength due to what it is called torsional case. This point you should keep it in mind. Now, we will solve one problem on modified Goodman diagram for fluctuating types of torsional shear stress case. So, this problem statement how it is, first of all I am just discussing the problem statement. So, a transmission shaft you see of cold drawn steel, this steel specification is given as like 27 Mn2. For this steel generally it has a ultimate strength the given data is ultimate stress is given as 500 MPa, okay, and yield strength is given for this material, that means for that shaft material is 300 MPa, which is subjected to a fluctuating torque with values varying from minus 100 Newton meter what it is called. So, here torque you can say minimum is minus 100 Newton meter and torque maximum is given as plus 400 Newton meter. This it is subjected to this types of torque. The factor of safety, so here factor of safety is given as 2 and the expected reliability is 90%. reliability is 90% also given. So, here we are neglecting just to show how to solve the problem, that is why we are not considering the stress concentration types of effect. So, here what we need to do? We need to determine the diameter of the shaft. So, we need to find out what is the diameter of the shaft. So, here we need to assume distortion energy theory of failure. For solving this problem, what we need to consider? Distortion energy theory of failure. This you should keep it in mind. So, we will solve this problem. So, what happens? How the problem is looks like little bit I am showing. So, let us consider this is a shaft, this is a shaft, circular shaft. Okay. It is subjected to torque T. What I am telling, understand? This torque T have a maximum value and this torque T have a minimum value. This is given. So, based on this data, generally what are the things we need to find out? We need to find out what is the diameter of this shaft. This you should keep it in mind. So, this for designing purpose, here we will use modified Goodman diagram for torsional case. Drawing modified Goodman diagram, first and foremost things we need what it is called endurance strength. So, first of all endurance strength due to based on Marine equation we know for you can say tensile types of case or you can say bending types of case is generally you can say Ka, Kb, Kc, Kd, Ke, Kg into as it is a steel material 0.5 into SUT. So, here everything is given, Ka is given as 0.79. Let us consider here the size, let us consider this diameter is varying from 0.75 to 50 millimeter within this range, let we are considering. If we consider this thing from the table in earlier discussion we know Kb value is 0.85. Kc is reliability factor is 90% is given. So, its value will be 0.897. Kd value is temperature effect parameter, it is neglected. So, its value is 1. Okay. And here also stress concentration factor K is also neglecting. Okay. So, other factor is neglecting, that is why what happens we are calculating like this. So, once we use what it is called distortion energy theory, there we will incorporate the value of you can say Kg. Kg due to torsional case, how the Kg value will come, that I will just show you. Okay. So, here generally this AC we are calculating, this is 0.5 into ultimate is given as 500. So, this will give us a value endurance strength equal to 150.58, 150.58 MPa. Okay. This is the endurance strength based on Marine equation, you know, this is I have already discussed these things, Marine equation. Okay. Now, we need to draw the modified Goodman diagram for what it is called torsional case. So, for that generally now step 1 is over, step 2 modified Goodman diagram now we will draw for torsional case. So, for torsion we will find for torsion. For that we know for a torsional case we know endurance strength due to shear. So, endurance strength due to shear, here we need to consider distortion energy theory. So, according to distortion energy theory generally SE endurance strength due to shear equal to 0.577 0.577 into endurance strength AC, whatever the Marine equation we are getting, this you should keep it in mind. Similarly, endurance yield strength due to shear S y I am writing, this also will be equal to your 0.577 into yield strength due to tension. These are the things you should keep it in mind. So, this will give us a value, that means endurance strength due to shear, this will give us a value 0.577 into 150.58, okay, and this will give us 0.577 into yield strength is given as 300. So, shear stress is given 86.88 MPa and yield shear stress is given as 173.1 MPa. These are the things you should keep it in mind. Why I am calculating? Because for drawing modified Goodman diagram in torsional case, these are the data required. That is why this information is required to find out. Now, here we need to find out what is the mean torque and what is called amplitude of the torque. So, for finding out mean torque, MT mean we know MT maximum plus MT minimum divided by 2. So, this will give us MT maximum is given as, I have already this, you can say T max or T min, you can see, you can write as this MT maximum, this is MT minimum is equal to T min, you can write. So, this will give us a value of 400 minus 100 divided by 2. So, this will give us 150 Newton meter. Okay. What is MT amplitude? That means torque amplitude, that will be MT max minus MT min divided by 2, that is actually your 400 plus 100 divided by 2. Why plus is coming? Because this 100 is negative. So, negative positive is coming. So, this will give us 250 Newton meter. Generally, for drawing load line, we know we need to find out theta value of that load. Tan theta we can write as MT amplitude divided by MT mean. So, MT amplitude divided by MT mean is 250 divided by 150. So, this is given as 1.67. Okay. So, from here we can get theta is equal to, directly I am putting 59.04 degree. Now, we will draw, based on this following information, we will draw the modified Goodman diagram for torsional case. So, for modified Goodman diagram for torsional case, now I am going to draw. So, in modified Goodman diagram, all of we are very well familiar now, because I have already shown. So, this is, you can say, tau mean, shear stress mean, and this is represent shear stress amplitude tau A, that is better to write, and there will be a horizontal line and there will be a inclined line of, or yield line, that is 45 degree, makes an angle with horizontal axis 45 degree. So, this O, A, B, C represent the modified Goodman diagram for fluctuating torsional shear stress. Now, we need to draw a load line. Let us consider this load line is OE, which makes an angle theta is equal to, I have already calculated, 59.04, 59.04. It's cut this AB line at a point let x. This will give us a value of what? You can say Sm due to shear, comma S endurance strength, this you can say, because this is a horizontal line, correct. So, that is why this x point represent a mean stress due to shear and endurance strength due to shear. These are the value generally we can get from here. So, here what is the amplitude or you can say endurance strength of this shear case, that idea we got. Okay. Now, so here generally you can easily find out what is the S amplitude, that means what is S endurance strength, or you can say this also you can write as shear amplitude value. How to find out these things? This is already I have calculated endurance shear stress, that is actually 86.88. How I have calculated, I have already shown, that is I have calculated generally 0.577 S of what it is called endurance strength. Based on this thing generally we have calculated this what is called S endurance strength. Now, using this we need to find out what is the permissible, what is called permissible shear stress amplitude. So, here the permissible shear stress amplitude will be what? Permissible shear stress amplitude tau P A, I am writing permissible shear stress amplitude. This will give us S A divided by factor of safety. So, here S A is generally here endurance strength, already I have find out due to endurance strength divided by factor of safety. So, this will give us a value of what? This will give us a value of, directly I am putting these things, 86.88 divided by 2. Now, this shear stress due to torsion, for we know for pure torsional case T by J equal to tau divided by R equal to G theta by L. These are the things is very well known to you, where T is the torque, J is the polar moment of inertia. So, here I am writing this, J is polar moment of inertia, T is torque, tau is torsional shear stress, R is the radius of shaft, These are the things is very well. G is called shear modulus, theta is called angle of twist, and L is the length of the shaft. These are the things very well known. So, I am not going to discuss about all these things. So, from this equation we know tau is equal to T R by J. What is J? Polar moment of inertia in case of circular case, J equal to pi d to the power 4 divided by 32, generally half of, you can say 2 times of what it is called area moment of inertia. Pi d to the power 4 by 64 is the area moment of inertia, that is 2 times is pi d to the power 4 by 32. So, that now I am going to put here that value. So, here tau will be, you can say T amplitude, here in this case tau permissible amplitude will be, you can say T amplitude you can say MT amplitude, R is we need to find out, and j is we need to find pi d to the power 4 divided by 32, or you can write capital D by 2. Okay. This we can write, this diameter we need to find out. So, if we put this all this value here, what are the things we are getting? Tau pi we can write as mt amplitude into capital D by 2 divided by pi d to the power 4 divided by 32. This will give us 86.88 divided by 2. So, from here we can easily find out what is d value. So, d value is given as 30.83, you can say millimeter. This is the design diameter of that shaft. So, if we use this much diameter of the shaft, then what happens if it is subjected to the load or fluctuating torque is given for this problem, it will never fail. Now, here little bit I need to explain why this what it is called 0.77 is coming. These things you need to know little bit, that is why I am going to discuss little bit about that point, then it will be very clear to you, there will not be any confusion, you can say. So, in case of we know pure shear case, first of all what is distortion energy? So, maximum distortion energy you can write as, so I am writing this maximum distortion energy I am writing in case of what it is called 3-dimensional case, once it is subjected to 3 mutually perpendicular principal stress, that case we know 1 plus mu divided by 6 E, directly I am putting these things, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This is the, you can say, maximum distortion if it is subjected to 3 mutually perpendicular what it is called principal stress. Sigma 1, sigma 2, sigma 3 is 3 mutually perpendicular principal stress, this you should keep it in mind. For tensile case, here I am writing, for tensile case where generally sigma 1 is only there, but there sigma 2 and sigma 3 because equal to 0. Why? Because in unit tensile case generally your structure is subjected to only unidirectional loading sigma, other 2 direction there is no load. That is why here you can say only one maximum stress you will get. So, for tensile case, tensile test case, you can say your sigma 1 will be there, sigma 2 and sigma 3 will be 0. So, for this case what is the you can say distortion energy we will get. So, distortion energy for unidirectional tensile case UT case I am writing, this will give us 1 plus mu, mu is here I am writing mu is Poisson's ratio, Poisson's ratio, E is Young's modulus, E is called Young's modulus, or it is also sometimes called modulus of elasticity. So, this divided by 6C. So, what are the things here we will get? Sigma 1 minus 0 square plus 0 square plus 0 minus sigma 1 square. So, this will give us a value of 1 plus mu by 3 E into sigma 1 square. These are the things is very well known to you, correct. So, in case of yield criteria, what we used to do, we generally equate. So, here generally we equate this 2 equation, let this is equation number 1 and this is equation number 2. Here in case of yielding, generally you can say this sigma 1 equal to sigma yield during failure. So, what we can write, if we equate this 2 equation, we will get maximum distortion energy failure criteria, or it is also sometimes called von Mises Ill criteria. So, von Mises Ill criteria tell the component will fail if this is equal to equation 1 is equal to equation 2. What I am telling, and then you can say it is subjected to fail, where sigma 1 will be your, in this case equation 2 will be yield strength. So, what are the things here we will get? So, we will get 1 plus mu by 6 C is equal to into sigma 1 minus sigma 2 square. For your understanding purpose, actually I am just doing all these things, because you should know suddenly how I use 0.577 that value. Okay. That things you need to be clear. So, this will give us for yielding purpose, this will be equal to whatever the value you are getting, you can say this sigma yield square. So, this will give us, you can say directly here I am writing, this you can write directly I am writing as, so here sigma y equal to, you can write square root of, here half will be there, okay, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. These are the things you should, this is called generally maximum distortion energy failure criteria, or you can say von Mises Ill criteria. What I am telling, understand? This is distortion energy Ill criteria that you can say. Now, in case of pure shear, where generally in case of here I am writing plane stress pure shear case, always you should keep it in case of pure shear case, generally for plane stress condition sigma 3 equal to 0, and there will be sigma 1 equal to plus tau and sigma 2 will be minus tau. These are the things you should keep it in. Generally pure shear state of stress, how it's look like little bit I am showing, then it will be more clear to you. So, here in this case generally pure shear case, the state of stress look like generally like this, what I am telling you. So, this you can equivalent, if you make a 45 degree, you can say here you will get sigma max, which is actually your equal to your tau, and there will be a sigma 2 or sigma mean value here, that is actually you can say sigma 2, this will be your minus, this will be actually minus tau, you can say this will be because compressive in nature. This you should, this is equivalent things I am just showing. So, here you can say sigma 1 in case of pure shear case, sigma 1 equal to tau and sigma 2 equal to, you can write as minus tau in case of pure shear case. So, this and what is called in case of plane stress condition, in case of plane stress condition sigma 3 will be 0. So, what is the distortion energy, what is the here you will get. So, distortion energy you can say, let this is equation number A. So, in this equation number A, by equation number A, what you can get? By equation A, what we will get? Sigma y will be equal to what? Sigma y will be equal to square root of half, here generally sigma 1 and sigma 2 is there. So, generally sigma 1 is tau, sigma 2 is minus tau. So, that will give us plus tau, okay. This is square, then plus here will be you can say tau 2. So, minus tau. So, that will be tau square, here will be another tau square. These are the things you should keep it in mind, okay. So, what are the things here you will get? So, this will give us a value of sigma yield equal to, you can write as 1 by 2, okay. This is 4 tau a square plus 2. So, 6 tau a square, this you can write. So, this will give us root 3 tau. Okay. These are the things you should keep it in mind. So, from here whatever the tau value you will get, that tau value is generally sigma yield divided by root 3. So, sigma yield divided by root 3, this is actually what, from here you can say write as 1 by root 3 is 0.577 sigma yield. So, this is yield due to tension, this is you can say yield due to shear, what I am telling, understand. So, yield strength due to shear is how 0.77 is coming, that idea you can get from this description, what I am telling, understand. This way generally I have used in previous slide for solving that problem, how this 0.77 is suddenly coming, this is the way it is coming, okay. This you should keep it in mind. So, these are the references which I have used for this lecture. Thank you.